I suggest we start speaking. 3 answers, great. 4, super. I guess it caused some discussion. So just in case, I will be really brief during this discussion as well, because we still have a lot to discuss. Nikolai also has some additional stuff for you today to speak about soft critic, which is really great. So here we go. Supervised, unsupervised, just in case, I guess everybody is fine. Learning underlying data structure is mostly fake. Actually, we do it everywhere, but in unsupervised learning, it's our main goal, I would say. And we never approximate reference answers in unsupervised learning because we don't have any reference answers unless we imagine them for ourselves, like in dimensionality reduction in PCA, for example. It doesn't require any feedback, correct? So no more questions. In supervised learning, we learn underlying data structure as well because we do it all the time, everywhere. We learn how to approximate the reference answers. That's why it's supervised learning. We need them, of course. Actually, it's kind of strange that these two bars are really not so correlated. And we don't need any feedback from the data because we assume our data is already fixed. We don't affect the distribution we're dealing with. So reinforced learning, instead of that, learns on the experience we gained so far. We learn not to approximate reference answers, but to get some feedback on our actions and get something by trial and error, and so on. And of course, all these 3 areas, reinforced learning, unsupervised learning, and supervised learning, are kind of interconnected. So we always learn some underlying data structure. In reinforced learning, we can use some part of the experience from some kind of expert, Grossmeister, and so on, so to pre-train our model. In supervised learning, sometimes we can switch from supervised learning to reinforced learning, like we did in NLP, and so on. So they all are kind of interconnected. Markov assumption. We assume that our conditional probability distribution in the reinforced learning setting of future states of the process depends only on the present state and action. Of course, that's kind of true. And if we speak about dependency on the unlimited history, it's not a Markov assumption. Just in case, when we are speaking about dependence on fixed number of steps in the past, it's still Markov assumption, just of high degree. So not of degree 1, but 3, 2, 5, 10, and so on. Any questions so far? Just in case, I can see the chat, so you can either speak orally or write something in the chat, and so on. Okay, so cross-entropy method, we learned it on the really far away first lecture, and we recapped it several times. It learns the conditional probability distribution of actions given states. Actually, we do that all the time in any particular policy-based, I would say, methods on policy methods, because we try to affect our policy directly. All right, so here we go. State value function, V function, we discussed it before. It shows us expected total reward, absolutely true. No more questions, I guess, in here because it's completely right. Yeah. State action value function, great. Zero entropy, great answer. It's expected total reward if we make action A and then follow policy P. High correlation between states close to each other is a problem if we're speaking about continuous action states, yes. And it's not a problem if we're speaking about discrete state action situation, because then we just have a table which represents our policy, and different locations in this table are completely different. So if we change one location, we don't affect the other location, so that should be fine. Okay, because we have here one answer which is stating that it's a problem as well. All right. Oh yeah, and just I love this expectation. So expectation of a maximum compared with the maximum of expectation. Of course, when we're speaking about expectation of a maximum, wow, I guess actually we'll need to prove it, because it's true that expectation of maximum dominates maximum of expectation, because we can select just, okay, actually I can even show it. Just let me open something. Moment. Just in case I want for everyone to see it. So here we go. Here it is, for example. Let's say we have such sample like 1, 1, 1, 1, 1, and so on, for example, for 100 times, 1000 times. And we have 100, it's A. So A, here it is. And B is the same stuff, for example, where we have 200 in here. So NP array AB. So here we go. If we compute the maximum over first axis, we get this. And if we compute mean, so average, we'll get 150. If we do it otherwise, so we compute C mean over first axis, and we then compute maximum, we get something close to 1. You see? So when we compute first maximum, we ignore all the smallest values. We pay attention only to the maximum values. And then we simply compute mean over all the maximum values. If we first compute mean, we take into account all the values in general, and only then compute maximum. It's get back. It's really important because when we are speaking about Q-learning, we can face this problem, because if you remember, when we compute the loss function for the Q function and the Q function itself, in there we have the mathematical expectation and maximum as well, and it causes the overestimation problem. Just everyone who answered on this question, please check that you are fine with it, everyone who hasn't as well, and then give me some feedback, please. I insist. Anyone? Clear? Okay, super. Thank you. And just in case, when do we need it? When do we use it? When we face this problem? Once again, when we have some Q values, when we select the action with the highest Q value, we actually can get the situation when we overestimate the Q value because we incorporate some noise in here, and that's kind of a problem. So correct statements. On policy can learn off policy. No. Off policy can learn on policy. Yes, it can learn on anything. On policy methods require some experience replay buffer. Actually, they cannot use experience replay buffer unless we assume that we haven't changed our policy a lot. So really small experience replay buffer is still on this same policy. So be careful with it. Model in model-free learning. Looks like, I don't know. There is some country with such flag. I can't remember which one. I guess they were the Norway colony back in the history. Okay, so model in model-free learning is the model of the environment, of course, the environment model, because we always need the agent model. Otherwise, we don't have any kind of policy and we cannot interact with the environment. So be careful with it. Policy gradient allows to optimize the policy directly to maximize the reward. Great. 4 out of 4. Advantage looks like great, absolutely correct. And sorry, I have duplicated this question, so my bad. So, all right, actually looks really great for me. So we don't have any specific deep problems in any of the areas we covered so far. Just be careful with simple math, because simple math can be still a great deal in many different areas. So any questions from you right now, just in case? No. Okay, 3, 2, 1. Okay, and then I have only one question to you right now. Then I actually will provide a word to Nikolai because we discussed it in the chat while you were solving the warm-up test. So just try to clarify for yourself. Is it clear how to use policy gradient? Let's say just simple reinforce in case of continuous action space. Just try to overthink it. If you think it's clear, just say clear, write it maybe. If you don't think it's clear, then say it's not clear as well. All right?
Could you please repeat the question?
Is it clear how to use reinforce in case of continuous action space? So if our action space is discrete, it's kind of obvious. But what about continuous action space? All right, I guess everybody is thinking. All right, so according to the silence in the chat, I assume that it's not quite simple to understand it, so I will try to explain it briefly. All right. Dear students, anyone? Yes, we can assume that neural network is a function which is providing us actions. So just in case, here is the blackboard. So let's use it, our update on our parameters. So when we compute our log likelihood, sorry, our reward. So what do? We have our omega t plus 1. It's just omega t plus alpha learn rate multiplied by the gamma, not gamma nabla, logarithm p omega of action conditioned on state multiplied by the reward of state action. Correct? Any questions with it? Any problems with this formula? Is it correct? People, anyone? Looks okay. So when we assume that our policy discrete provides a probability in the discrete action space, so it's some kind of distribution, like I don't know, multinomial. then it should be fine. Action 1, action 2, action 3, action 4, action 5. So just on the technical side, in our neural network or any other model, at the end, we have the softmax, which is providing us the probabilities, which are just right here. Okay, clear. But what if our action space is continuous? So for example, we have our action space in which we have some, I don't know, angle, which we should, according to which we should rotate the joint, like the right arm, for example. This alpha is the angle our network is providing. So here it is. How should we estimate the probability of our action? So we cannot use the softmax at all at the end. So we need to do it somehow otherwise. Any ideas on that?
Probably introduce some prior distributions over actions and try to learn the parameters of its distribution.
All right. So with
entropy.
So for example, we assume we have some kind of probability distribution like normal, for example, with mu and sigma, and our alpha is coming from this distribution. Then actually our model will be predicting mu and sigma. All right. And then the log probability actually.
I'm sorry, but I don't see what you're writing.
Sorry. Yeah, I just switched to another desktop with accidentally. So we have some kind of distribution from which we are sampling our action. Here it is. Here is our action. But instead of predicting the action itself, we predict the parameters of our distribution from which we sample our action. Okay, so here it is actually. And then to compute log p theta a condition to S, actually in here I'm using omega, not theta, just to be consistent. We remember the formula of our probability distribution. So actually it will be logarithm of some constant. It's 1 divided by 2p sigma blah, blah, blah. I guess you all remember the probability density of the normal distribution. Plus, actually minus, it will be minus 1 divided by 2. In here we have what? We have the action minus mu divided by sigma. And the all should be squared. Yeah, something like that. So here will be our log probability, and it completely depends on the distribution we selected for our policy to be actually connected with. So we selected prior normal distribution. We assume that we sample actions from normal distribution, which parameters are predicted by our model. And then we get these probabilities and log probabilities from this distribution. Just in case, is it clear or not? Because it's usually really complex for people just to switch from the classical discrete control environments to continuous control, because it just doesn't work at all. So just please think about it and tell me whether it's fine or not so fine. Okay. Clear. Super. Then actually, if you have any questions to me, I am here for you. Otherwise, it's I am giving the word to Nikolai. It's fine.
Radoslav, last time we discussed with Nikolai our homeworks, future one. And as you said, we were supposed to do one lab assignment about this Majoko environment. Will we get it?
Yeah, actually, I wanted to show it to you right now, but just in the meantime, I will just send the notebook after the webinar with Majoko environment, because I wanted to show you the baselines on the webinar, but Nikolai suggested to dive a bit deeper in the SAC, so I decided to give him the word.
Well, I think we'll have time at the end of the webinar, so I hope I won't take too much with my explanations.
Please don't be in a rush.
Okay, sure.
So I stop sharing and give the word to you.
Okay, so good evening from me. So I'm going to discuss a little bit deeper how can we apply deep reinforcement learning methods to continuous control. And it's just a happy coincidence that Radoslav came across the same topic. So I hope it will be very natural to switch from continuous control with policy gradient to what we'll cover now. So just a minute before, you've seen how we can apply policy gradients and policy-based methods which directly optimize the policy in case of continuous control environments, when the action space is continuous and not discrete. So what about value-based methods? Can we still apply value-based methods in this scenario, in this setting? And the answer is yes. And in some cases, value-based methods are more preferable, although they are not as common as policy-based methods. So just a quick reminder. Let's see which methods we are talking about. So what is the primary value-based method that we've seen in this course? Any suggestions? So you actually had a lab on this method.
Please don't be shy. Oh, yeah.
DQN, yeah. So what does DQN do? So DQN is a technique, an algorithm which combines Q-learning with deep reinforcement learning. So we have state space, we have continuous state space. That means that we cannot memorize Q functions for each state in a table, and we need to do something with that. And we do this with the help of deep neural networks. So for example, in most of the Atera games, states are images. So we feed images to a neural network and we predict Q values for a set of actions with this neural network. So let it be CNN. So we pass state an image tensor to convolutional neural network, and we predict a vector of Q values for actions, right? So this was in the finite world, which is very simple. And we optimized it using the temporal difference loss. So remember, temporal difference is when we use, instead of honest rollout reward for the full trajectory, we look only one step ahead, and we sum one step reward with the value of the next state. Yeah, so our objective, Q prime, is reward, one step reward, plus the discount vector multiplied by the value function for the next state, or which is the same, maximum over all Q functions for the next state. And to optimize our neural network, to optimize our Q network, we use temporal difference loss, which basically brings the estimate for this starting state for Q value for the corresponding action that we took to the Q prime, which is the temporal difference Q target. So we use TD loss, or which is the same MSE loss. So we minimize mean squared error between the predicted Q values and the reference Q values, which are given above. Yeah, so I hope this makes sense. I hope this reminds you of something. So this is training. And what do we do at test time? We predict Q values and we simply select the action with the greatest Q. So our policy is not explicit, so it's implicitly derived from the Q network. So we have Q network, which predicts, which can predict utility for each action, and we select the best action as the action with the best utility, right? So this is the discrete case. And if we move to the continuous case, where action space is not discrete, where it's continuous, for example, real valued, it's not as simple. So do you have any ideas right now? What can we change to use the same architecture, the same training process to predict actions in the continuous case?
Can you repeat again?
So the question is how to apply Q networks in the continuous action case. So how can we predict continuous actions, real valued, using the Q network architectures? So the problem is that we don't have.
Yeah, we use expectation over the previous, how to say, accumulated experience.
So can you expand it a little bit? So which experiences in expectation?
We already made few steps, so we know like a policy EA versus S, which we used, and we know rewards which we got.
Yeah, so you mean that we can train a policy which is another function apart from the Q function, right?
Yes, if I remember correctly.
Yeah, and how can we train this policy? So what is the objective for training?
Maximization of reward.
Well, that's not exactly value-based in this case. If we train policy directly on maximization of reward.
Yeah, I see.
So this looks like policy gradient.
Yes.
So there is an algorithm which solves this problem. It's called DDPG. It was introduced short time after DQN was published, so it's it goes as DDPG, which is deep deterministic policy gradients, and it's not the same as policy gradient. It's much more close to DQN, and let's see what this algorithm does under the hood. So first of all, there is a slight change in the Q network architecture. So before, we had a Q network which took only state and outputs a vector of Q values. Now we no longer can do this because we have infinite number of actions, and this vector will need to become infinite sized, which is impossible. And to avoid this, we parameterize this function as a function of two arguments, state and action. So we pass state and action to, for example, CNN again, or something else. And we predict only one value, Q of S and A. So now we can predict Q values. And most of the rest of the training process isn't changed. So we sample trajectories, we estimate one-step reward, and then we employ temporal difference loss with MSAI training objective. So there is one more question: how to compute the action? How can we compute the action A prime here in the Q prime term? So let's phrase it in a different way. So we need to compute ground truth Q prime, which will train our Q network to be closer to. So here is a part of the trajectory, state, one step, reward, and the next state. And we want to bring Q of S and A close to R plus gamma times the maximum Q of all Qs from state S prime. Yeah. So we imagine that we select the best action from the next state among all the possible ones. And hence we need to compute somehow the argmax over Q from the state S prime. And here is a little problem. So we have continuous action space, and to compute the argmax, we need to have argmax over continuous number of actions. Of course, there are some approximate methods, like you've seen them in the optimization course, but it's first quite slow. And second, well, to do this with high precision is not very trivial. And the solution is that aside from the Q function, we introduce the policy function. So first of all, we have Q network, and the second component is the policy network. So policy network, which will be called mu of S, this network will be kind of the controller for our agent. So we will have Q function which will estimate the utility of action, and we will have a policy network which will estimate which action to take. So kind of similar with actor critic, you may say, where critic was Q function, Q network, and vector was the policy itself. So here we have Q network which estimates Q values, and we also have a policy network which will predict which action to take. So now it's, I guess, more straightforward. So we know how to select actions, and we know how to train our Q model. What's left for the complete algorithm? How to train policy network. And actually, it's quite simple. We'll train policy network to select actions with the greatest Q. So policy network will be trained in the following way. So its loss function will be 1 over n, sum over states, q of s, mu of s. And we want to maximize it. So we kind of have firstly Q function, and then we train our policy network to select actions which will maximize Q values. So we have history of states, and we want our policy network to select actions which will bring higher Q values. And this will give us kind of an approximation to argmax from the discrete case. So I guess that there may be some questions here, as it's not very trivial. So please feel free to ask questions now. It's a good time for them.
So we use two networks simultaneously, right?
Yeah.
And at every step, we run one, and after that, another. One, another.
During training, yes. During inference, we use only policy network.
Yeah, okay. So it's like expectation maximization.
Well, from a very distant perspective, yes. So other questions, or if you understand it, please write in the chat. No questions. Okay, I see that someone is fine with the DDPG, sorry. So I think that we can, to strengthen the understanding, we can look at the implementation from spinning up repository. So just to see the whole picture. So what is the training doing in this algorithm? So we train simultaneously Q network and policy network. So Q network is the same as before. It predicts Q values for different actions in different states. And it trains by gradient descent using partial trajectories and temporal difference with one step look ahead. Yeah, so firstly, we observe history of states, actions, rewards. So we play some games, we track states, we track actions, next states, rewards, and all the rest of the stuff. So when it's time to make an update, every, for example, every n steps after playing, we look at our buffer, we take some batches, and we make an update for our networks given our batches. So first of all, we compute targets. In my notation, it was Q prime. Here it's called Y, and it's one step reward plus gamma multiplied by the value function of the next state. Yeah, so here's Q target is target network. You are all familiar with this. Target network is the frozen copy of the trained network. So we have targets, and we want to bring our Q function close to the target. And we train it by gradient descent using mean squared error. As simple as that. So this is the complete update for the Q network. So now it's time to train policy network. And policy network is trained with gradient ascent to maximize the Q value of the selected actions. So we want policy network to select those actions that have high Q value. So it's kind of the surrogate for argmax, which is not exact, but trained with gradient descent. So it works fine. It works in some environments quite with high quality. And you can think of this as a simple extension of DQN for the continuous control environments. Right. So that's DDPG. Sorry, there is some lagging in Zoom. I don't know why it doesn't want to share. Yeah, now it's working. So I'll quickly cover some extensions to DDPG, which make this algorithm more robust, more applicable in any scenarios, because the standard DDPG has some disadvantages. So on the most part, those disadvantages are connected with the stability of training. So it turns out that DDPG suffers from some problems of DQN, like overestimation problem, when the estimated Q values are much larger than true Q values. And also it suffers from general stability issues, like when for some reason policy network and Q network kind of become entangled with each other in a strange way that damages the quality. So there are two very widely known extensions to DDPG. And first of them is called twin delayed DDPG. Or in short, there is, in some cases, it's referred to as TDA3, not to be confused with temporal difference. So twin delayed DDPG is very very similar to standard DDPG. So I'll just point out the differences between them. So this algorithm addresses some issues with the stability of training, and the first modification that it employs is double Q-learning, and not simple double Q-learning, but clipped double Q-learning. So I don't know if you remember this webinar, but we've talked a little bit about double Q-learning. So if you remember what is the difference between simple Q-learning and double Q-learning, please go ahead.
As I remember, it has two heads, I guess.
Yeah, not exactly heads, it has two Q networks. So, yeah. And what is the purpose of two Q networks? So why is it better to use two networks instead of one network? Well, it addresses the problem of overestimation. So before, we saw a problem that Q values tend to be much larger than true Q values from the neural network. Q of A is much greater than Q true. So there are some issues in training which contribute to this problem. In particular, the main issue that if somehow at some stage of training some action gets Q which is optimistic compared to the truth, then this action will be selected much more often, and the rest of the actions will be underexplored, so it will be not very likely to change. And to address this issue, double Q-learning trains two Q networks. So it has Q1 of S and A and it has Q2 of S and A. So those networks are trained simultaneously, and they are trained on the same target. So they, in theory, should do exactly the same. And the main key here is that in target, in Q prime, we use the minimum of those Q networks, of those double Q networks. So our target will be R reward plus discount factor times min of the value functions given by those two Q networks. And that's it. So the main principle here is that once we now have not one Q network, but two Q networks which should do the same, but due to randomization, they are different. So if one Q network is accidentally, if one Q network accidentally becomes optimistic for some actions, and it shouldn't, then the second Q network will kind of smoothen this effect and fix this mistake, because we take minimum of them and we tackle the overestimation in this way. So that's the first modification, and it improves the convergence by tackling the mentioned problem. The second modification is quite small, but it contributes to the improvement also a lot. And it's called delayed policy updates. So delayed policy updates means that we train policy network and Q network simultaneously, but we update them with different frequency. So before we made per update for Q network, we made a mirroring update to policy network. So we made step for Q network, then we made step for policy network. So the number of updates was absolutely equal. And this brought some problems because the update to policy network could change the actions made by our agent, and hence make the subsequent updates for Q network less effective. So I don't know if this explanation was very clear to you. So I think that we can make it simpler just by saying that training process becomes much more stable when policy is being updated rarer than Q-network. Because if the policy is updated very often, then Q-network becomes kind of lagging behind the policy. And for example, if the policy is being updated once per 10 steps, once per 5 steps for Q-network, then it smoothens the training process. So I don't know how to phrase it more clearly. So if you still don't understand, please write in the chat.
In twin delayed, these are two identical nets initialized with random parameters, and the difference is only in the random, like, stochastic gradients, right?
Yeah. So the objective for double Q networks is the same.
Okay.
So delayed policy updates means one policy update, one Nebula policy network per n Nebula Q. So this makes it simpler for Q network to train, because if we change policy network very often, then Q values which corresponded to the previous policy network weights will become kind of stale, and this hurts at the training. And the final modification is called target policy smoothing. It's a little bit connected to the previous webinar in terms of exploration. So target policy smoothing is basically introducing exploration to our network. So the main purpose is to add noise to the predictions from the policy network. This may seem very natural, but standard DDPG does not do that. So let's look at the complete picture of the training procedure for TD3. Hopefully you'll understand it better than now. So the general course of the training is relatively the same as in DDPG, the same as in Q-learning. So we first of all record some sessions, store them into the buffer or into the replay buffer. So all of those algorithms are of policy, and this means that we can train on the experiences from long before now. So first of all, we record history. Then when we need to update, we sample batches. Then we compute target actions. And as you see here, we introduce some noise to the outputs of the policy network. So we select A prime of S prime not as mu of S prime. We add some normal noise and we clip the result to be valid. So it's connected with exploration. So this noise makes it possible for agent to deviate from the current optimum, because the current optimum may not be the best optimum. And to enable agent to explore the environment a little bit and to see what's in the neighborhood is generally very profitable. So we compute target actions with exploration, with noise. So now we can compute targets, and here in computing targets, we use our double Q networks. So we have selected target actions, then we take the minimum of them, of the Q values, and this is our target Q from the trajectory, from the partial trajectory. And now we have everything that we need to make a gradient update to Q network. So we use MSAI loss, and we update our function to be closer to the temporal difference target, to Q target. And then we update our policy network if it's time to update it. So it's done every so often with a fixed period. So that's it. And that works much more stable than simple DDPG. So if you have any questions, please write them in the chat or ask. I'll wait for a few seconds. Okay, so we have about 10 minutes remaining, so I don't think it would be sensible to talk about soft act critic, because it will take much longer. It's quite a complicated algorithm, so let's summarize the main points here. Sometimes we want to apply value-based methods instead of policy-based. And the main reason for that is their sample efficiency. So policy-based methods are not very sample efficient. It means that to train them to reasonable quality, you need a lot of samples. And you need to be able to quickly collect these samples if you're training on policy. So in policy gradient, if you need to make an update, you need to play some sessions with the current policy. This is fine if you have some kind of simulator, or if the problem is not very connected to the real world, like Atari games or games in general. But if you don't have the opportunity to have a simulator, or if the feedback is very slow, or if it's expensive to collect samples, then there will be some problems with that. And you'll probably need to use more sample efficient algorithms. And off-policy methods are typically more sample efficient, because to train them, you can use experience from not only the current policy, but the previous experiences, or experiences not connected with your policy at all. So for example, if you're training a chessbot, you can download the games from some database from the past century and train on them. And if you use off-policy methods, then you can use those experiences, those sessions. And this is the main advantage. So in our course, the main off-policy method that we have seen is Q-learning. And for the more realistic algorithms, that corresponds to DQM. So the problem was that we could not apply DQM to continuous action spaces. And today we have seen the examples of solution for those methods. First, DDPG, which is DQM with some building over DQM. So it's DQM plus policy network, which selects actions. As simple as that, you can think. And DDPG sometimes fails to converge. sometimes there are some problems with hyperparameters and the sensitivity and so on. So there is an extension that's called twin delayed DDPG, which addresses those issues by three main modifications. First, double Q-network. Second, update target network, update policy network, sorry, with some lagging. And third, which is exploration. And it works better in most of the scenarios and not as sensitive to the parameters. So basically, that's what we've discussed right now. And that's it for my part. If you don't understand something, that's perfectly fine. Just go on and we'll discuss it. All right, it seems no questions, at least for now. So I'll pass the microphone to Radoslav, and you can discuss the homework assignment.
All right, thank you, Nikolai. So actually, everyone, once again, any questions from your side? If you have some, please just share them. Otherwise, let's move on slightly to the upcoming days. Okay. Okay, 3, 2, 1. Then let's go. So first of all, I want you to open the website along with me, because right now I want you to check the MuJoCo environments and the MuJoCo original website as well. I've sent the links into the Zoom chat, and I will duplicate them into the Telegram chat as well. One moment. Here we go. So let me share my screen just in case. Here we go. So here is the MuJoCo website. So I've sent it to you. And as I already said, MuJoCo is a really great environment, actually not only environment, but physical simulations. Backbone, not backbone, I don't know actually how to name it, engine, which allows you to run many different beautiful environments. You can see them on my screen right now. So there are several of them. We recently used some classic control problems like curveball, which we used a lot, really a lot. Some of you tried with pendulum as well. There is acrobat and so on. But MuJoCo is much more interesting because it allows us to solve continuous control, first of all. Then it gives us an opportunity to build some models for relatively complex structures like ant. Actually, it's not quite ant, but something close to 4-leg spider. Half cheetah, half because it has only 2 legs, and actually everything is 2-dimensional. Hopper, actually a leg which is trying to jump. and so on. Somebody who is dancing breakdance. Actually, the main goal of this humanoid is to stand up. Just original humanoid which learns to run, and you've seen it on the first reinforced learning lecture, and so on. So these environments are really it would be correct, I guess, to say that they're really state-of-the-art environments right now, because most of the papers, recent papers, novel papers in reinforced learning are being benchmarked on MuJoCo environments as well, if they're speaking about some continuous control. And that's why we want you to interact with them as well, because it's really useful. Thanks to the society, MuJoCo now is open source, and we can use it under FH2 license for research, for some actually educational stuff, and just get some experience. And thanks for the society once again, because we can actually run the MuJoCo even in the collab or on the machine, which I will provide you today after the class ends. I will just send you the form which you need to fill to get the access to the lower-end server at MIPT. It has about eight GPUs, 2080 Ti with 11 gigabytes of video memory for every of them. So it should be kind of fine. So just in case, I would like to share the notebook with you. Right now, it's only on the collab, because I want just to show it to you. I will upload the notebook into the repository as soon as it's get just a bit cleaned, because I've been trying to make it work with different environments and it took some time. But still, just in case, what I want you to see. I want you to see that actually MuJoCo environments are well incorporated into the OpenAI Gym API. Actually, they are part of the OpenAI Gym. So you can simply interact with them using all the same APIs we discussed before, and all the same APIs you used in the second lab assignment, first lab assignment, and so on. So if you follow the link I sent you into the chat in the Telegram or into the Zoom chat, you can actually see that all the imports are kind of all the same. MuJoCo for Python is actually really easy to be installed. Actually, I will install it on the lower-end as well, so you don't. I hope I will install it on the lower-end, because I'm not sure I have all the admin rights in there. So in that case, you even won't be needed to install anything by yourself. But otherwise, after you just follow the link I sent you, you can see that MuJoCo environments are completely same in terms of interaction. You can just create the environment after you collected all the necessary libraries and get all you need in here. Let's just give it a moment to fulfill everything it needs. Yeah, here we go. So here is the inverted pendulum, for example. You can interact with it somehow, all the stuff we discussed before. Like in here, we made a step to the left. But just in case, when we're speaking about MuJoCo environments, most of them are continuous control, and that's why we've been speaking about continuous control today. So for example, now we can use, for example, step 1.4 to the right, and you can see it will go to the right afterwards. 200, 300. Yeah, it should be. And so, and you can select any other of these environments, actually, like inverted double pendulum and so on. So you will have actually a second upcoming, next lab assignment, which will incorporate 2 steps which are mandatory and 1 additional step, which is actually not mandatory, but optional, like the home assignment on the question answering. So speaking about the lab assignment, the first part of the lab assignment, like in the previous lab, will be to train simple model, actually any kind of the model, either something based on DQN or something based on policy gradient or A to C for the inverted pendulum, because it's the most simple approach. and it will be just necessary for you to get ready to interact with the Mujok environment. Just in case, the inverted pendulum is this one environment, so you just need to balance the pole like we did in the cart pole. And the second step will be to deal either with half cheetah or ant v2. I would say that half cheetah is much more easier, and I would recommend you to start with it. But if you want some for brave and true, you can deal with the ant v2. The third part, actually optional part of the assignment, will be to deal with the humanoid and learn it to walk. It will be really complex, just saying, because it's not simple to make it walk. And it will be an optional assignment which you can actually select, up to you. So that's kind of it about the stuff. I will send the notebook with the inverted pendulum for everyone later this evening, where you can actually start training your model. And if you want to get some better results, you can interact with more complex environments. And next time we will actually try to apply one of the approaches we learned today to the environments we see right now. Okay, so any questions are appreciated. And here we go. And the deadline is like before. So the deadline will be for this lab assignment. The deadlines are actually 1 day before the exam, which will be on the second week of the February. Okay, we will provide the exams will take place at first 2 weeks of, yeah, we'll provide it actually tomorrow, I hope, because we need to discuss it with Nikita and then just send it to you. Okay, super. So, any more questions? Three, two, one. Then take your time and see you soon. Goodbye.